So basically around every real number there are its own infinitesimals. So for example, I consider the number 2, then star 2 is the equivalence class of the constant sequence 2. But if I consider 2 plus 1 by n, then that is its own infinitesimal, right? Because 2 plus 1 by n minus 2 is 1 by n. Yeah, so this is called, I mean, these sets are called the set of infinitesimals around star x are set to form a halo or a monad. These are just names, but there is some structure around every real number. So this is called, so yeah, maybe I should call this the image of I is known as the standard real numbers in star R. Okay, in hyperreals, what are standard reals? They are precisely those which are in the embedding of real numbers into hyperreals. So anything which is of the form star x, that is a standard real number. Yeah, that's how we can talk about our actual real numbers over there. And then what is the non-standard part around a standard real number? That will lie in this halo or monad. Yeah, if you have some number, let's say 2 plus 1 by n, that sequence, the equivalence class of that sequence, then 2 plus 1 by n's standard part is 2, star 2. Yeah, and the non-standard part at that point is 1 by n. Yeah, the difference between them. Okay, so that's how you set up the language. And one more thing, say that y in star R is bounded if absolute value of y is less than star n for some n in n. You understand this? Some real number, some hyperreal number is bounded. I mean, maybe this notation is a bit confusing. Let me write it again. If absolute value of y is less than star n. Okay, star n means the corresponding standard natural number. Its absolute value you can compute. You just make everything non-negative, every entry in that sequence non-negative, right? So that sequence has to be less than star n. Can you give me one example of something which is not not bounded, I should say finite. Bounded is also a name which is used. Can you give me some example of not finite? The sequence n. Yeah, the sequence n diverges, so therefore it is not finite. So we can only do this standard and non-standard business for finite hyperreals. Yeah, otherwise we do not talk about it. Any questions? You all look lost.
So what is this absolute value for mod of y?
Absolute value is the actual absolute value, you choose any representative, any sequence of real numbers which represents y, then you take mod of every single entry. Yeah.
And if each element is less, the absolute value of each element is less than this star.
Yes. Yes. Actually, I mean, to be more technical, what I should say is that given a sequence, if you change the indices corresponding to a u small subset to 0, then can you get this? Can you get this property? Yeah, that's important. Yeah, it's not necessary that, so suppose my sequence is 0, 1, 0, 2, 0, 3 and so on that we saw yesterday. Yeah, and it is 0 at every even number. But if even numbers are, I mean, this sequence looks like it has a divergent subsequence, right? 0, 1, 0, 2, 0, 3, 0, 4. It has a divergent subsequence, but that doesn't matter because odd numbers are not large. So you can change all the odd entries to 0 and then the sequence itself is 0. So even though it looks like it is going towards infinity, it's not. It's actually a finite hyperreal number. It is 0. Yeah. So lot of things can be done. And why are we, I mean, talking about this? Can we actually do calculus over here? Yeah, I mean, I'm not going to show that exact statement, but there is something very important over here, and that is called transfer principle. Now, loosely speaking, what is true? So, a property is true in R if and only if that property is in star R. Now, this is the loose transfer principle. It says that whatever you can do in R, you should be able to do it in star R and vice versa. But I mean, this is a loose property. How should we make it precise? We are talking about predicate logic, first order predicate logic. So we should say that a first order sentence is true, yeah, precisely speaking, yeah, for any formula, any sentence phi in the language of ordered rings, yeah, language of ordered rings plus dot minus 0 1 less than, yeah, that is the language of ordered rings. R satisfies phi if and only if star R satisfies phi. So, do you remember any example of phi for this, like something interesting? Some first order property of real numbers?
All perfect squares are positive.
All the?
All perfect squares are positive.
All perfect squares are positive. Yes, yes, that's a property. One simple property is that addition is associative. Now, addition is associative in real numbers, and therefore, with the help of transfer principle, we know that addition is associative in hyperreals also. Yeah, and the definition of continuity. Definition of continuity. What is that definition? If two numbers are infinitesimally close, then their images under that continuous function are also infinitesimally close. Now, can you express this property properly using the language of real numbers? Yes. Normal epsilon delta definition. How do you express infinitesimals? You can add a bunch of statements. See, x minus y, mod of x minus y, you want to talk about two numbers being infinitesimally close. Mod of x minus y is very small. Well, okay, just wait. Perhaps let's do some more mathematics, hardcore mathematics, and then come back to this. Okay, let me postpone it for now. Okay, so our main goal today is to reach the statement which makes this transfer principle very precise. I mean, this is precise enough for reals and hyperreals, but we want to formalize this whole process for any arbitrary language, not just language of ordered rings and not just for one particular structure of real numbers, ordered field of reals. We want to do it in most generality as possible. Okay, so I am going to start with something different now. So, let us talk about okay, so now this is the fresh start, and the notation, if you have understood the concept of addition, multiplication and less than for real numbers, hyperreal numbers, then only you can follow this properly. Yeah, the notation will become bad really fast. It will become complicated. So, let L be a language, a predicate language. Let I be a set, non-empty set. And Mi, I in I, be a family of L structures. Okay, so we have been given a bunch of L structures. The first thing that we should do is to define what is the product structure. The product structure written like this. Now please pay attention, I am writing curly M everywhere so far. Has as the underlying set or the universe the set product of capital MIs. Do you remember what is product of arbitrary product of sets, non-empty sets? Somebody? Set of choice functions. Okay. So this is, I am going to use the letter H. H from I to union of Mi, I and I, such that for all I in I, H of I belongs to Mi. Yeah, this is the set of choice functions. Okay. Yeah, you can see why this compactness theorem and Walsh's theorem is really the last thing that we are doing. We are using everything that we have studied so far. Yeah, we are also talking about arbitrary Cartesian product. Okay, and how do we define for each M-array relation symbol R? When do we say, and well, I should be given a tuple, yeah, tuple H1, H2, Hm in product of Mi, I and I. Please recall that we write the tuple A bar belongs to M. We do not write A bar belongs to M to the power size A bar. Yeah, this is our model theory standard. Okay. So, for each M array relation symbol R and H1, H2, Hm, a tuple from this product, a tuple of M tuple of choice functions, say that H1, H2, Hm belongs to R product of Mi, this is curly Mi, its interpretation in the product structure, if and only if, can you tell me what? If and only if H1I, H2I dot HMI. Now remember, H1I belongs to Mi. So this tuple belongs to the interpretation of the relation symbol R in the structure Mi for each I in I. Okay, so this is not difficult, but it takes time to get used to it. Okay, so a tuple of choice functions is in the interpretation of the relation symbol in the product structure if and only for each I we have the individual components, they are in the interpretation of R. Okay. Now, if F is an n-array function symbol and H1, H2, Hn belongs to product of Mi, I and I. Here I am not using curly Mi's, I am only using capital Mi's because I need to access elements. Then we have to talk about the interpretation of F in the product structure. Now here it is curly Mi because it is the structure that we are talking about at H1, H2, Hn. This is defined to be the tuple. Yeah, what should we do here? Tell me. Loudly, Gopil. What can we do? So, what are H1, H2, Hn? They are choice functions. So, we actually need a choice function. This whole thing, this whole interpretation, we again want to land inside product of Mi. So, we need a choice function. So, like defining it like this is not really enough. We should say this thing evaluated at I is equal to Now this is simple. The interpretation of the same function symbol in the component structure Mi at H1i, Hni for each I in I. You understand? This is a choice function. So we started with n choice functions and we want to obtain one single choice function as the output. So given these inputs, this is the output. So this is a choice function. So evaluated at I, it must be the only natural thing that we can do. Okay, and finally, if C is a constant symbol, then what is the interpretation of C in the product structure? Well, it has to be a choice function, because it has to be a single element of the product set. So it has to be a choice function. So when you evaluate it at I, then you will get the interpretation of this constant symbol in Mi for each I in I. Okay, so we haven't really done anything complicated. Yesterday all of you understood how to define addition and subtraction of sequences of real numbers. Everybody was saying component wise. Okay, so now component wise has this definition more generally. It's just that we are not just talking about sequences of real numbers only. Our each entry in the sequence could come from a different structure. So that's why we have to use a slightly sophisticated language of choice functions. Make sure you read this properly. Okay, this is because now I am going to introduce one more thing, and that is an ultra filter. Okay, so far what we have done, what was given, L was a language and I was a non-empty set and Mi was a family of L structures. Now I am going to choose an ultra filter on I, which means an ultra filter in the power set of I, and I will define the ultra product of this family. Okay, let's do that. So now suppose U is an ultra filter. I am not giving you examples for the product structure because I have already given you examples. Okay, product R square, then product R to the power n, they are all examples of this. Suppose U is an ultra filter of on I. Okay, then define the ultra product of the family Mi, sorry, curly Mi, I in I, with respect to the ultra filter U as follows. The notation for notation for ultra product is going to be product of mi, I in I, modulo u. The universe of the ultra product, because I have to describe everything, is the product structure, this you know, this much you know, the product of all the underlying sets, but this product modulo tilde u, okay, where what is tilde u? It has to be an equivalence relation, and the fact that it is an equivalence relation will be checked by you as an exercise. I have done that for the hyperreal construction. So tell me, what should I start with? What are two different elements of this product structure, product mi? Sorry?
Elements coming from two different structures.
No, not elements coming from two different structures. It's an equivalence relation. I mean, a priori, it's just a relation, binary relation on the set this. So, what are elements of this? Choice functions, very good. So, where I say that for h comma h prime in the product set, h is u related to h prime if and only if, I mean this is a definition, so therefore I will not write if and only if, I will just write if the set of those indices such that hi is equal to h prime I, this belongs to you. We have done this yesterday, yeah, in a much more simpler way. Yeah, so two choice functions are equal if they agree on a large subset of the index set. Okay, so this is the definition. Now, once we have the underlying set of a structure, what else should we do? How to make it a structure? Preserve all the symbols? No, we have to define the interpretation of all the symbols. Okay, so let's do that. So I'm going to start with a new board. Yeah, if R is an M-array relation symbol and H1, H2, Hn, Hm is coming from the product structure, then say that, now what should I say? That these are the elements, this is a tuple from the product structure, not from the ultra product structure. So I should say that the class of H1 comma the class of Hm, because unless and until I attach this class notation, it's not an element in the universe for the ultra product. Say that this belongs to R product mi modulo u I in I. So the interpretation of the relation symbol R in the ultra product structure, if, okay, what is the next thing to do. Okay, let me show you quickly what we did here. We said that over here H1, H2, Hm is in the product structure if for each I in I we have this individual tuple in Rmi. Now we cannot expect it to be true for each I in I. We should only expect this to be true for a large set of subset of index set. So we will write that. Okay. If now I am choosing a representative. Okay, so H1 let me write it properly. If the set of all indices such that H1I comma HMI, this thing belongs to Rmi and the set of all such indices is in U. So this happens for a large set of indices. Okay. Here there is something to be proven. What is to be proven? This is well defined, yeah, because H1 can be U equivalent to H1 prime. Yes, so I am going to write this as an exercise. We have done this exercise in the special case yesterday, but I want you to still do it for this most general case. So exercise, if H1 is U equivalent to H1 prime and so on, Hm is U equivalent to Hm prime, then show that the above is well defined. Okay, so in this second part, you are supposed to replace this H1, H2 up to Hm by H1 prime, H2 prime, Hm prime, and then use the properties of ultrafilter, yeah, that intersection whenever the set of all indices where H1 agrees with H1 prime and H2 agrees with H2 prime and so on, the intersection of all of them must be inside the set where the whole tuples agree, the set of indices where tuples agree. So, yeah, I mean, please try to write this down. It is actually simple, but only if you practice it. Okay, so let's get back to the definition. If F is an n-ary function symbol and H1, H2, Hn is in the product structure, then we have to define the interpretation of the function symbol f in the ultra product structure I in I modulo u at the equivalence classes Now this is going to be a choice functions equivalence class. Okay, this whole thing has to be an element in the universe for the ultra product. So the equivalence, U equivalence class of a choice function, single choice function. So I should define it at I to be What should I show it, write it to be? The only thing I can. It must be the interpretation of the function symbol f in the component structure mi, and then I have to give it inputs from mi, and those inputs are coming from h1i, h2i up to hni. Okay, so this is for each I in I. Once again, there is an exercise. If H1 is U equivalent to H1 prime and HM is U equivalent to HM prime, then show that F interpreted in the ultra product structure at the equivalence class H1 U HNU. Now this whole tuple is U equivalent to F interpreted in the ultra product structure at the H1 prime class up to Hn prime class. Yeah, because whatever we wrote here, we use that on the right hand side. So if I change the right hand side to H1 prime, H2 prime, Hn prime, then my ultimate choice functions, both choice functions, they should be equivalent. They can't be equal. They just have to be equivalent up to U. So that's what I am asking you to show. Okay, and one final thing which is very easy to say, if C is a constant symbol, then the interpretation of C in the ultra product structure has to be a choice function. Yes, so evaluated at I, this choice function evaluated at I is this. For each I in I. Okay, here there is no option. Yeah, I mean, you can still take its equivalence class. Okay, are you getting what's happening here? Well, I guess you are getting it's complicated, but okay, you actually have to get your hands dirty. You have to write these things down. I have already uploaded the next tutorial sheet long time ago. So please go and check those problems, and that will help you. I mean, I have given you the main problem that show that all these three things are well defined. Yeah, because well definedness is perhaps the most important property. You can see how everything is coming together. We are using the notion of equivalence relation very heavily. We are also using the notion of a congruence relation because it has to behave well with respect to certain things, the algebraic operations. We are using ultrafilters, Boolean algebras, we are also using logic, right? Everything is coming together in this one single thing. Okay, so your discomfort will not vanish unless you write something with your own hands. I am just going to go ahead and state the main theorem. Okay, so that is called Walsh's theorem. It's a Polish name. Let me repeat. The L symbol is pronounced as V and the S with this accent is pronounced as sh. So, Wash's theorem. If you type, this happened in a previous batch. I just uttered the word Wash's theorem and then somebody came back to me. There is no such theorem. Yeah, because they typed in WASH. Yeah, unless you write it down, you won't know. So, Wash's theorem has two parts. Yeah, so do you remember dependency theorem and substitution? Yes, they were the long boring exercises. Okay. Now, Wash's theorem is also such a long and boring exercise. So, it will have two parts. What should be the first part? It is the theorem for terms. And the second part is the theorem for formulas. Okay. So, you can see how powerful it is. Suppose L is a language. This is precisely the formula version of Wash's theorem is precisely the transfer principle that we were talking about earlier. Suppose L is a language, Tx bar is a term, phi x bar is a formula, okay. Then I is a non-empty set, U is an ultra filter on I, Mi, I in I is a family of L structures, okay. Then first thing first, okay, so the interpretation of the term in the ultra product structure. Oh, yes, I think I can also, I can add something more, yes, just, and H1, H2, Hn is in the product structure, then, okay, then the interpretation of the term in the ultra product structure at the equivalence classes of the choice functions. Okay, this is a choice function, right, but it's also the tuple. This is a choice function, but it's also a tuple, right. So, therefore, this is U equivalent to the tuple, yeah, I mean TMI evaluated at H1I up to HNI, because H1I, H2I, HNI are all elements of MI. So, I can give them as inputs for the term, the interpretation of the term in the structure MI. Now, I collect this whole tuple for I in I. Now, this is a tuple and I take the equivalence class. Well, that equivalence class, I mean, so these two equivalence classes are actually equal. They are U equivalent. Okay, so this is the first statement for terms, and the second statement is for formulas. Yeah, so So the ultra-product structure satisfies the formula phi at a tuple. So a tuple has to look like this. If and only if the set of all indices such that the component structures Mi satisfy phi at H1i, Hni is a U large set. Okay, so this is a large set. Now, just as a corollary, I am going to write down. So this is the transfer principle. Yeah, you are taking a formula, that validity of a formula or truth of a formula in the ultra product structure depends on whether that structure is true on an average, whether that formula is true on an average in the individual component structures. So the set of all indices such that phi is true in Mi, yeah, that determines it. So as a corollary, just bear with me. So corollary, if theta belongs to SL, then the above statement is quite simple. Then the ultra product structure Mi satisfies theta if and only if, what should I say? It is a sentence. So sentence doesn't have any free variables. So therefore this x bar component, that's going to vanish entirely. So if and only if the set of all indices such that Mi satisfies theta is large. In particular, if Mi is equal to M for all I, just like we had for hyperreals, yes, then we denote product of Mi I in I by U by the notation M to the power I by U. So you can see hyperreals were defined to be R to the power natural numbers modulo U. Yeah, so we are coming back to that. If all the component structures MIs are the same, then we use this notation and call it an ultra power of M. Yeah, this is not just a power, it's an ultra power. We are not doing superhero stuff though. Yeah? Okay. So finally, what does this corollary become in that? So M to the power I modulo U satisfies theta if and only if the collection of I such that Mi satisfies theta. Well, does it make sense? M satisfies theta is in U. So if and only if what? M satisfies theta. Now this is our transfer principle. Let me take you back to slide number 2 quickly. We said that R satisfies phi if and only if star R satisfies phi, and that's precisely what I have written here as a consequence of Walsh's theorem.